will open this, and here I will press, where am I here? Where'd it go? Oh, there it is. That, and that should do it. Let's see. Okay. Now I'm also going to pull up the assignment. I suppose that would be helpful. All right, so we got 9 out of 14. Nine out of 14. What is 9 out of 14? It is 64%. So we got 64% of the class to complete the assignment. All right. So for you 35% of the students, this is your chance to follow along. For the 65% of you that did it, this is your chance to follow along and review your work. Again, don't bother submitting it. If that's what you plan to do after class or today or tomorrow, I will not accept. Just don't bother. Not once I've fully gone over it and done all the problems for obvious reasons. All right. But I'd really strongly encourage, kind of had the same conversation with some of my honors class just now. Some of you to really consider where you're at as a student this year. This is me speaking again to students at home and in class. No one in particular, just a general conversation for you to think about where you're at, what you've been doing, how you're doing. I do have some students that are really struggling primarily with homework, really struggling. And that's, a major concern at this point where we're pushing 30 assignments so far this quarter. And for some students, 10, 15, 20 of them have not been handed in. Just being honest, just having that honest conversation with you, and you should have that honest conversation with yourself. Just like, what's going on? If that is me, why am I here in the first place? This is an AP class. What I mean by that is what was my goal? If my goal was to do well, then, put together a plan for doing well. If my goal was to just pass the AP exam and just try to learn some physics, then put together a plan for that. I can't imagine anybody's plan was to fail. But for students that are not doing work, you will fail. You will fail the class for the year, and you will not pass the AP exam. I can guarantee that. In 15 years, I've never had a student that could get away with not doing any work, pass my class, and pass the exam. It's just never happened, not once. So all I can do is encourage students, as I again looked and saw that 65% of my students were given Saturday, Sunday, Monday. So how much long? You're given 3 days, 3 full days to do this assignment. And 65% of my AP students were able to step up and hit that pitch, while 35% didn't even step up to the plate. Again, it's concerning, and I've had those concerns for some of you all year. And as we round that corner and kind of look toward end of quarter one right now, all I can do is say, you're going to need to probably put together a plan, and you're going to have to try to make it something work for you. For some students, it's again, for some students, it's always been a concern just in terms of getting work done. And now compound onto that this idea that you're at home every other week. For some cases, there's nobody there with you. And so for some students who already struggle with getting assignments done and you're home for a week, this is a real recipe for disaster, to be quite honest. And at the end of the day, you guys aren't little kiddies anymore. You guys are grown adults at this point. You need to start thinking this is my opportunity to kind of prove to myself and my family that I am an adult. I'm a young adult, but I am an adult. I got this. I can do this. Because for some of you, again, that are juniors, some of you are seniors, some of you are going to be in college soon, perhaps next year. Reminding you that there's no professor that's going to come knock on your door. There's no person that's going to say, why weren't you in class today? There's no teacher or professor that's going to say, you didn't hand in that assignment? Why not? In many cases, they won't even know your name. You'll be a number. You'll be number 70 out of 354 students in a lecture hall. And the reality is, at that point, you're paying $100 per class for many, many students. If you're paying $50,000 a year, which I don't recommend doing, but every year students will sign up for that, $50,000 a year. That's $100 per class. You really need to start reflecting on, again, are you ready for that? If you're somebody that, again, is really struggle with getting work done consistently, maybe, maybe not. I mean, if you turn things around this year, maybe I'd say, yeah, go for it. But if by the end of the year you can't turn that around, I'd say you might want to consider holding off on college for a year or two. You might want to just, I don't know, just kind of dig your feet in a little bit and really come to better understand yourself before you start throwing away $100 a class, because that's a lot of cash. So again, same conversation with my period 5 honors class, same one with you guys now, because I think it's important as we continue to move forward each day with our window of time rarely extends beyond a day or two for us, right? Usually we don't think beyond one day into the future, maybe 2 at the most. Usually it takes somebody else to encourage you to think about like a week from now or a month from now, or God forbid, a year from now. Few people in your life challenge you to even think about that. I'm one of them. I'd encourage you to have those thoughts for yourself often and frequently, maybe not every day, but maybe at least once a month. That self-check-in, like where am I at and where is this going? What were my goals in the first place and am I reaching them? Again, it's one thing to assess yourself in general. It's another to be able to identify what issues you might need to deal with. A second piece. It's quite another to, once knowing those issues, put together a plan, and yet quite another to actually execute that plan. For people that are able to do all 4, good for you. For a lot of people, it takes a lot of effort. For many people to go through their entire adult life and they'll never actually get those skills. They'll go through their entire adult life and they will never be able to do those things that I just said. And has nothing to do with school. You want to be one of those people. You want to be somebody who's constantly reflecting and thinking, what can I do to become better? And we don't expect you to be perfect. We just expect you to want to be better if there's room for growth. We want that for you. Especially, again, I'm talking to AP students, the cream of the crop, right? You guys are the best in the town. So I hope you guys just consider that. Also remembering the year's still young. We haven't even reached quarter 2 yet, right? So if it was quarter 2 starting today, we'd be 25% of the way through the year. We're probably like 20% of the way through the year. It means you got 80% of the year left. So even if you're feeling defeated because of maybe some of the things I've talked about, there's plenty of time. There's always time. There's always time for you to think about those things and put together a plan. Just a reminder that I am available for extra help. If there are students that prefer to have extra help from me during the week, I would be happy to give it to you. Instead of the Friday, 12:30 to 1:45, just email me and I'll see what I can do. If it works better for you to do it on a Tuesday or a Wednesday, obviously it can't be from 12:30 to 1:45, but I am here generally from 1:45 to 2:30 every single day, Monday through Thursday. So if there's a time after school, but before 2:30 that you'd like extra help, instead of trying to do it on Friday, because, well, who wants to get extra help after a long week and it's Friday? Most people want to just be done, and I get that. So if you want to email me if you're thinking help might be a benefit, please feel free to do that. Help will definitely put you in the right direction. But you got to, again, make the plan and then actually do the plan. Not easy. Much easier said than done. I can guarantee you that. It's like the New Year's resolution. How many people actually stick with their New Year's resolution? I think studies have been done to indicate it's something like 10%, I think. 10% of Americans will stick with their New Year's resolution for more than 2 weeks. So that speaks to something about our culture and who we are as people. But doesn't mean that you have to fall into that 90, that percentage of people. You can change whatever you want and do whatever you want as long as you stick to it and you stay committed. And as young adults as you are, I'd encourage you to start thinking about those things now before having, rather than later. All right, I'm going to now review this assignment. Maybe once a quarter, I'll have that conversation with you. All right, what we're looking at is a frictional problem that involves a car skidding car. When a car skids and leaves a black skid mark, it's doing that because of a heat effect of heat, which, by the way, I haven't been using my microphone because it's been dead, but it's probably charged now. So the skid mark on a road is burnt. It's burnt asphalt, and it turns black. And to burn something, it requires heat, and the heat is produced by a frictional effect known as sliding friction. And it can be sufficient enough to reach, create those cause temperatures in those two surfaces. In this case, the tire, the rubber itself, and the asphalt, to reach high enough temperatures to burn. I mean, have you ever seen a race car just locking up its e-brake, and then at the real races, and then they start spinning the wheels, so-called burning rubber? And you see all that smoke, right? Burning. It's literally burning the tire. The tire is at a very high temperature. It's a frictional effect at that point, and the rubber is literally smoking because it's burning. So this is, again, friction has to do with rubbing, sliding, but it's always turning some of that motion energy into heat, and it thereby slows the object down, usually bringing it to rest, like a book that slides and stops, or a car that slides and stops. Okay, so the problem is going to be sketched up here. So this is where the car comes flying in. And I will actually increase the size of this. It's too small. Okay, and so at this point, it then will, and then stop somewhere over here. And this is where the brakes are applied. But we're not talking about just like your normal braking process where you just press the brakes. We're talking about locking up your brakes. Like literally there's somebody in front of you, you just jam on your brakes. When you do that, your brakes literally will usually, the anti-lock system usually prevents that from happening, and it pumps the brakes. The braking system will notice that you've slammed on the brakes. Before the anti-lock braking systems were manufactured and designed and created, slamming on the brakes would immediately lock up your brakes, and you couldn't do anything after that other than just hold the wheel until your car stopped. And that means during that skidding process, you're at the will of friction at that point. You can try to press your brakes while you're sliding, and it's not going to do anything. They're already locked up. If you were outside watching that car, you'd see the wheels are not turning. It's literally the wheels are stationary while the car slides across the pavement, locked up. Now they know that you can get more force from your actual brake pads than you can get from the dragging effect of your tire against the asphalt. And so to prevent that from that locking effect, they've created anti-lock braking systems, which when you slam on the brakes, instead of allowing your wheel to lock, it provides a quick pulsing action on the brake pads, and you're able to get more stopping force from the brake pads that are pulsing and pressing against your wheel. The wheel will continue turning while you're slowing, but you'll end up having a shorter stopping distance than locking up the brakes and then just sliding due to friction. That would normally cause a longer sliding distance. So in an effort to make cars safer and give you shorter stopping distances, the anti-lock braking system was designed long ago. But just letting you know, otherwise, especially if you're on a bike and you just slam on your brakes, it's a frictional effect, right? So this would be called the stopping distance. Technically, I guess it would have to go from front of the car to the front of the car. This is called the stopping distance. All right, and then the first question says, draw a free body diagram. So our free body diagram has to identify any forces, again, that the object feels. Usually it's best to think, what are the things that are in physical contact with the vehicle? If it's touching the vehicle, then it's applying a force. There'll be a force between the vehicle and it. So what's touching the car? Yep. What is it? Yeah, the ground is pushing which way? Up. Yep, that's called the normal force. The ground is preventing it from falling. We know that the ground isn't only pushing up. What also is the ground doing during the slide? Yeah, good job. Nicely done. So the frictional force, which is going to be written as K for force of kinetic friction, is to the left because the velocity is to the right. We've drawn it sliding to the right. So the frictional force is the other direction. So the ground, can the ground exert multiple forces in multiple directions at the same time? Yeah. The ground is not only pushing up on the car, but it's the sliding effect on the ground is providing a leftward force simultaneously. The same object, the ground, the asphalt, yep. Asphalt can put multiple forces on you in multiple directions simultaneously. The reason I've drawn this, does anybody know why I drew this force of friction vector, the magnitude smaller than the normal force? I did that intentionally. Does anybody know why? A little louder. I can almost make out what you're saying. That's right. So let's tackle that part. What force would be down? Gravity. And how long would I draw that? Yep, equal in magnitude to the normal force. These are canceling. These add up to 0 because they're equal in magnitude, opposite in direction. So now that we've seen this one, why is this frictional force shorter than this one? Why would I not have drawn it longer than the gravity force vector? Remember that the magnitude of the frictional force in magnitude, the physical quantity amount of frictional force, it's always a percentage of your weight, of the object's weight. Because if the coefficient of friction is less than 1, like 0.6, then the frictional force is 60% of your weight. And therefore, this vector, if drawn perfectly, would be 60% as long as this one, because this represents your weight, right? Fg is your weight, force of gravity. So for that reason, I've drawn it like that, because I believe the problem says the frictional coefficient is actually, it says 80%, so it would actually have been made a little longer, but I intentionally made it shorter. If the coefficient of friction was the number 1, then the frictional force would be equal to whatever you weigh. 1 times your weight. The frictional force would be 100% of your weight. If that were the case, the frictional force vector would be equally as long as the weight vector. If the coefficient of friction was the number 2, very rare, but possible, that means the amount of sliding friction force you're getting is 2 times more than whatever you weigh. In which case, this would be 2 times longer than the weight vector. Also, just FYI, in the real world, air resistance is always there. Like we never talk, we rarely talk about it in AP physics because they just don't want it to overcomplicate things that are already complicated. But realistically, of course, when you're driving a car, that air resistance is pressing up against your windshield, right? There's air molecules floating like this. And when your car is flying along and slams into them, the air molecule will feel a force to the right on the air. The windshield puts a force to the right on the air, right? You're just sitting there floating in the air and a car comes over and smashes you, then you're going to feel a force in the direction of the car's motion to the right. But Newton's third law actually says that if there's ever a force on one thing, there must be a force on the other. That forces come in pairs. They can't come in singles. Forces come in pairs. Force requires 2 objects, 2 things, and both objects will feel the same amount of force, but opposite in direction. So if the windshield is hitting an air molecule and pushing it to the right with a certain pushing force, then that air molecule, again, that would be right when they connect, and it actually hits. In that same moment, the air molecule will be pushing backwards on the windshield with an equal amount of force. The air force on the windshield will be equal in magnitude to the force the air feels forward. The car feels equal amounts of force, but backwards. So I'm just pointing that out. In the real world, that college level, you would have that drawn here as another vector saying the drag, we call that air resistance or drag. It would be added as a leftward force. Both of those frictional forces under the tires and the air work together to slow your vehicle down and bring it to rest. There's no forward force. Reminding you of that. And you're just, there's no force forward. There's just, and you're already in motion. You already have momentum in that direction. That forward motion is just your motion that's already there. Object in motion stays in motion. Newton's first law. Object rest stays at rest unless there's some unbalanced amount of force that causes it to either speed up or slow down. In this case, there is an unbalanced force, right? This is unbalanced. For it to be balanced, there would have had to be a forward amount of force equal to that amount. Then we'd say those cancel, it's balanced. When I said over here, these add up to 0, that means they're balanced. The vertical forces are balanced, so there's no, what I would say is there's no net force in the vertical direction. The net y component force equals 0. Because when we're adding up forces, we want to do it either all vertical or all horizontal. This is what we mean by the sum of the vertical forces. F net in the y direction is these two. These add up to 0. But we couldn't say that same thing for the left. There's no left and right. There's only one left force that's unbalanced. And what does Newton's law say? Second law says, well, if there's unbalanced forces, it's either going to speed up or slow down. It's going to slow down. It'll speed up if the extra unbalanced force is in the same direction of its motion. Then Newton said, well, it will speed up. It'll accelerate at a rate equal to the unbalanced amount of force divided by the mass, F over m. A equals F over m, F net over m. Or Newton said, or if the unbalanced amount of force is in the opposite direction of the car's motion, it will slow down or decelerate at a rate equal to the unbalanced amount of force divided by the mass. Again, A is F over m, regardless of whether it's a speeding up scenario or slowing down scenario. Part 2 said, calculate the weight. The force of gravity is the weight of the vehicle. That's what it said. You need to know that your weight, all objects' weight, is the gravity, Earth's gravity force, weight. We were told that the mass of the car was 1,200 kilograms, and we know G is 9.8. 1,200 times 9.8. I get 11,760 newtons. Is vehicle's weight. FYI, just for your own knowledge, if this is an interesting topic to you and you might become an engineer someday, 4.4 newtons is equal to 1 pound. 4.4 newtons of force is equal to 1 pound of force. So if you divide something's weight in newtons by 4.4, that would give you the weight in pounds. So if I did this amount, 11,760 divided by 4.4, I get 2,672 pounds. So it's about 1.25 tons. 2,000 pounds is 1 ton, right? That's just a extra bit of information that's not necessary. That's number 2. Number 3 then says, determine the magnitude of the sliding friction force during this braking process, during the sliding process. It's not really a braking, like it's not a controlled brake. It's just a frictional effect between the road and the tires. But by the way, it's worth noting that even if you're pulsing your brakes, it's still a frictional effect between the brake pads and what's called your rotor. Like when you look down at bikes, when you're biking, you see these little things with the pads, right? Like a mountain bike. With these 2 little pads that stick out, and then you got your wheel that goes in between, right? And you know that when you sit there and press your front brakes, these 2 pads squeeze against the tire, and they rub right along the rim on both sides, produces heat, and it slows your bike down. You probably noticed that back when you were 6 years old, right? It's the same thing. My point is that cars have the same exact idea, the same exact mechanism. You have a wheel, and there's a rotor. If you look in that area, you'll see these shiny pieces of metal that are circular. It's called a rotor. And on both sides, you have these pads on both sides of this rotor. So when you pump your brakes, these pads now squeeze against the spinning rotor, which is made of metal, and it produces high amounts of heat and friction, and it slows the wheel down because the whole thing is one spinning system with your wheel. So if the rotor slows down, the tire slows down, your car slows down. Just pointing out, it's still a frictional effect, right? Both cases. All right, so number 3 said calculate the frictional force in magnitude. We would write it this way. The physical quantity of kinetic friction force in magnitude, just the amount, meaning we don't care about the direction. We know it's opposite of velocity, but when this is magnitude, we just want the amount. We would write it like that. It's the coefficient of friction times the force of gravity, whatever that amount of force of gravity is. We were told that the coefficient of kinetic friction was 0.8. Back in the problem, it said that right in the beginning, right there at the end. Coefficient of friction mu k is 0.8. Remember that 99% of the time coefficients are less than the number 1, most cases. And the weight we already had. I just calculated it. It was where did I put it? There, 11,760. This is newtons. I will point out that the coefficient of friction is unitless. Just the extra FYI. Just a coefficient, right? Coefficients are always unitless. No, a coefficient is a number that goes in front of something else mathematically, like y equals 5x. 5 is the coefficient to x. It's unitless. Usually coefficients are unitless. I'm not to say that all coefficients are unitless, but in a lot of cases they are. At least in physics. Coefficients in physics a lot of times are unitless. Not all the time. Anyways, I'd have to just do that out. So what do I have? 0.8 times 11,760, enter. I get 9,408. So we have a frictional force that's almost as much as it weighs. I will point out, if the braking force is exactly as much as it weighs, then it's going to slow down at a rate of 1g. When the unbalanced amount of force you feel, whether it's in the direction of your motion or against the direction of your motion, is regardless. When the unbalanced amount of force you feel is exactly equal to your weight, you will accelerate at a rate of 1g, 9.8 meters per second squared. So if you were in my chair on these wheels and I pushed, assuming that there's very little frictional force, let's just say that's true on the wheels area, and I just pushed you down the hallway and pushed on the back of your chair with whatever, 150 pounds of force, assuming that you weigh 150 pounds, you would accelerate at 1g. I would have to run with you, pushing and running with you, and you would gain about 10 meters per second of speed each second as we went down the hallway. That assumes you weigh 150 pounds. If I pushed on you with 300 pounds of force, you would accelerate at 2g's. You'd gain 20 meters per second of speed each second as you go down the hallway. It's the same thing for the slowing. If this amount of force is exactly equal to what it weighs, it would slow down, the car would slow down at a rate equal to g, meaning it would lose about 10 meters per second of speed for each second until it stopped. Or if you have a coefficient of friction that's 2 times what it weighs, wow, that means you can decelerate at a rate of 2g's. Your car will stop real fast. It will slow down and lose 20 meters per second of speed for each second that it goes. That's the idea there. Coefficient is important. It controls how long it takes you to slow down. Problem 4, provided all the assumptions already stated regarding the forces acting on the car, what is the net force? This is the net force, right? If I went back to my picture, I could say that the gravity force, the weight of the object was 11,760. If I wanted to add numbers here just to make it super clear, the normal force is how hard the road is pushing up on the car from the road in equal amounts. And the braking force is now to the left in the amount of 9,408 newtons from the friction. So if someone says, what is the net force? This can be thought of as negative if you wanted to. It's nothing wrong with thinking of it as negative since it's down. This one can be thought of as plus since it's up. What do those add up to? Those cross out, right? These cancel. The unbalanced extra amount of force is this. And you can call it negative if you want. The net force is equal to the kinetic friction force, which is equal to negative 9,408 newtons. Negative, again, just meaning it's a leftward force. All right, that was actually number 4. Number 5, derive a formula for the deceleration rate during the skidding period. I provided help to students for that at home, and maybe you used it, I don't know, but I provided some pretty specific hints. Now this is how that works. Just remember that Newton's second law is the idea that something will either speed up or slow down at a rate equal to this ratio, equal to how much force is being provided, unbalanced net force is being provided to it, and acceleration is inversely proportional to the mass. So if it's a heavier truck, more mass is gonna slow down at a slower rate. If it's a little bike, like my kid's bike with a little bit of mass, then it can speed up or slow down really fast because it doesn't have a lot of inertia. That's why these are inversely proportional. Makes sense to have them on opposite sides of an equation, one in the denominator, one in the numerator. That's how math works. If they're both in the numerator but on opposite sides, then that's indicating a direct proportion. Acceleration is directly proportional to the net force, and acceleration is inversely proportional to the mass. Those are the mathematical relationships that Isaac Newton stated. In fact, you could just go here and say Newton's second law. Newton's second law. No? Oh, this hasn't been Newton's second law. Sorry, my mic has been a little further away. Oh, sorry, that's not working. We'll try here. Newton's second law. Right there. The net force is directly proportional to the magnitude. It says the net force is directly proportional to the magnitude of. Sorry, I'm not reading that correctly. It says the acceleration of an object is produced by a net force is directly proportional to the magnitude of the net force in the same direction of the net force, and the acceleration is inversely proportional to the mass of the object. Straight from Google. And that's what we're saying here is a mathematically being represented. What I've shown here is a mathematical representation of those two ideas. So we already said we knew what the net force was, yes? Oop, on page, right here, we had the net force. The net force is equal to the force of kinetic friction. Okay? So the net force is equal to the force of kinetic friction. The force of kinetic friction is equal to the coefficient of friction times the amount of normal force, which is why if you were to press down on an object, like a book, and provide more pressure underneath the book because you're pressing down on it, pushing it into the surface that it's on, and then tried to move it sideways left and right while pushing down, you'll experience more frictional force because there's more normal force. There's more pressure in there for those little nitty-gritty teeth to rub against each other sideways. On the other hand, if you were to slightly lift up on something and try to move it left or right, the normal force would be reduced, and therefore the frictional force would be reduced because there's more gaps in there between the little nitty-gritty holes and bumps and valleys for each surface. And since there's more of a gap between them, they can more freely move left or right. There'd be less friction, right? But for all cases when we already said that the normal force is equal to the weight, we already said that, right? And we know that the weight is equal to mg, then the normal force must be equal to mg. Normal force is equal to whatever you weigh, right? If you're standing on a floor and someone says, what is the amount of force from the floor up onto your feet? Whatever I weigh. I weigh 200 pounds, 200 pounds. If I weigh 900 newtons, then the floor is pushing upward on me with 900 newtons if I'm standing on 2 feet. So we just plug that in. The normal force is mg. This is the expression for the net force. It's also an expression for the frictional force. This is the frictional force, again, this is the sliding friction force. It is the net force. Yeah. So now we're going to plug that in for net force. Acceleration is equal to the net force divided by the mass. We've got the net force. And I put mg in parentheses just to remind you that that is one quantity. It's the weight of the object. Net force divided by the mass. Mass over mass cancels. Shocking. Not intuitive at all. Therefore, the rate, how rapidly it will slow down while it skids, is equal to a percentage of g. That's all that's left. Since mu k is usually between 0 and 1 in most cases, then it's a percentage, right? So it's like the acceleration is, it really can be thought of as a percentage of g. If that acceleration is due to friction. And it doesn't matter if the acceleration is an acceleration or a deceleration, which means when you run, for example, what force actually propels you forward when you start to run? If you were in this hallway right now with your sneakers and that tile floor, and I said, go ahead, run, what force is actually propelling you forward? As you push off, what force is actually propelling your body forward? Friction. We know if it was made of pure ice that you wouldn't be able to, you'd slip on your rear end, right? Smash down. Your foot would just slip out and your body would fall. So we know friction is actually the force responsible for moving you forward. True. It's the force responsible for moving everything forward, including cars. Therefore, nothing can accelerate at a rate greater than g if the coefficient is actually less than 1. If the coefficient underneath your sneakers is 0.5 when you're in the gym, then you can't possibly go into a sprint and accelerate, even if it's only for 1 second, accelerate for 1 second at a rate greater than 0.5 g, if mu is 0.5. If it's a dirty floor, maybe that's the case. You wipe your sneakers, if you're an athletic person, you know, wiping your sneakers all of a sudden gets you more ability to accelerate. Because as soon as you wipe your sneakers, you're cleaning all of the debris that's filled these holes, allowing there to be more of a traction between them, because you've just wiped your feet with maybe sweaty hands in the best case, and then they'll really wipe them clean. Now the coefficient goes up to 0.8 or 0.9. Now you can accelerate at 80 or 90% of g. Again, for most things, since most things don't have coefficients greater than 1, even for car tires, I think the coefficient is like 0.9 for most car tires. It means that no cars can accelerate greater than g, at a rate greater than g. Even your drag races, as long as the coefficient is less than 1, they can't accelerate at a rate greater than g. That's the theoretical maximum acceleration rate. It's limited by how much traction is in here, and that's what is a reflection of this number. Just pointing that out. Again, all a little extra for you. You wouldn't get from a textbook. That is the formula for the acceleration, amount of acceleration due to friction. All right, now I go back over. Now that we have it, it says if we had car tires that had, number 6, twice the coefficient of friction, by what factor would the sliding distance stop by? So now let's talk about the sliding distance part of this. The best formula to have used is this one, as I had described in my hints. And so if your car was here, and then your car stops here, this is the start, you know, brakes applied here, and then your car stops here, then the delta x, the displacement, is from here to here. That is the stopping distance. Delta x is the distance represented there. A, we now know, is mu k times g, because we just showed that. Acceleration rate or deceleration rate. It really should be, by the way, it could be thought of as negative. If they asked for the magnitude of that, you would just drop the negative and write mu k times g. But negative because the acceleration is to the left, while the car is actually moving to the right, slowing. As long as remember that the acceleration is in the opposite direction of velocity, then that's true. All right, so what would the final velocity be when it stops? When your car stops, your final velocity is 0. 0 because it stops. When something stops, it has no speed. And the initial speed is whatever speed it has when it was flying in right before it jammed on its brakes. That's the initial velocity. So we end up with a formula after just plugging in 0 for the final velocity because we know the car stops. And now we're deriving a formula specific to this situation. Plugging in mu k times g in for the acceleration. Delta x stays, 2 stays. Technically, this is a negative here. Like I said, the negative mu k times g. And technically, I could move this over to the other side, and I'd have negative v initial squared. There's a negative on the left side and a negative on the right side, so those would cancel by dividing both sides by -1. And the negatives can therefore just be dropped. And you'd end up with v initial squared equals 2 times mu k times g times delta x. This is now a product of 4 things: 2 mu k g delta x. The question asked us to solve and analyze theoretically the formula for stopping distance, which is this is stopping distance. So that means we should solve for it. We should solve the formula for stopping distance. So that means I would need to divide both sides by whatever's next to it. I want to, this is just regular algebra. I'd have to divide both sides by 2 mu k g on both sides. 2 mu k g g g. Now I've got myself a formula. This is what we talk about when we say derive a formula. I've created a formula for the stopping distance of a vehicle, assuming that we know how fast it comes in before it jams on its brakes. And we also know the coefficient, which we talked about being such an important part of how rapidly something speeds up or slows down. Because that rate of how quickly it speeds up or slows down will affect how far it moves before it finally stops. If it slows down at a very low rate, it's losing speed, but kind of slowly, like a puck sliding across ice where mu is like 0.1, then delta x is going to be huge. It'll slide a huge distance before it stops. A low value here is a high value here because they're inversely proportional. Or a large value here, if you're sliding on sandpaper where mu is very high, then this will be small because they're inversely proportional. Slide on sandpaper, you'll slide a small distance. High value for mu, low value for stopping distance. And don't forget about g. So that is the formula. And we can now see the proportion. It said, what would happen to your stopping distance if mu k was twice as much? So that means it's asking us to look at the stopping distance and compare it to the coefficient. My rules for teaching you how to do these problems, this type of problem, which much of America struggles with, even at college level, is to follow, again, these general rules. You have a formula that has the 2 things in it, like we did, stopping distance and mu k, because that's what the problem said. It said, by what factor would the stopping distance change if mu k doubled? If that's the case, and you're looking at those 2 things, get them on opposite sides of the equation. Mu k and delta x are on opposite sides of the equation. Cross out all the other things. And then what are you left with? You're left with delta x is inversely proportional to mu k. Right? So it's a stopping distance is inversely proportional to the coefficient of sliding friction. What does inversely proportional mean? It means if one thing doubles, the other thing doesn't double, that's directly proportional. Inversely proportional means if one thing doubles, the other does the opposite or inverse of double. The opposite or inverse of doubling is cutting in half. So if mu k goes up times 2, doubles, delta x goes down times 2. That means you'll stop in half the distance, right? If you can double your coefficient of friction, that double twice as much traction while you slide, your stopping distance will cut in half. That means your car won't go 50 feet before it stops. It'll actually go 25 feet. Wow, that's a huge safety benefit. Of course, that's why they work so hard on these kinds of things. So that's the answer to that. The stopping distance would cut in half. Down times 2 means divide by 2. It's divide by 2. Delta x would divide by 2. All right. Let's see what other questions we have. That was number 6. If this exact scenario was to play out on the moon where there is less gravity, would the sliding distance be the same or different? Either way, why? What does the formula derived that we just created say about this question? Which is, again, you could do this experiment with a car and asphalt and get it up to a certain speed, slam on the brakes, skids, stops, measure the sliding distance and measure that skid mark. Now let's head to the moon. Take the same car with us. Let's head up there. We'll land on the moon, build the same asphalt, drop the same car down, get up to the same speed, slam on your brakes. There's the skid mark. Will it be just as long as the skid mark was on Earth? Will it be longer than the skid mark was on Earth? Will it be shorter than the skid mark was on Earth? That's what the question's asking. And either way, why? Let's just think about it conceptually. What does gravity do? Does it pull you down? Down? Yeah, right? I'm just going to point that out. If this is a box here and there's some gritty surface underneath it, if you went to Jupiter where there's more gravity, it would pull down really hard, like Jupiter's gravity. It would be a really strong pull. If that pulls down really, really hard, you might think, well, that means there's more pressure in between this gritty area. That should probably make more friction because it's pressing those two surfaces in here together tighter. Or if you went to the moon where there's less gravity, you'd think, well, that means there's not as much downward pull. It'll be a little looser in between, so that might be less friction. That's what most people would think, right? Let's go over to, where was I here? Okay. So here we have delta x is equal to vi squared. I'm just writing the formula that we had. You don't have to keep redoing it. You just look at the same exact thing. What does the formula say? It says that delta x and g, how are they related to each other? How does an effect of g, being a higher gravity environment or a less gravity environment, affect the stopping distance? Assuming that the car comes in with the exact same initial speed and we have the same tires and asphalt, so the coefficient is the same. Looks like it's an inverse relationship. Higher gravity, like Jupiter, less stopping distance. You'll stop more at a shorter distance. Or go to the moon where gravity is less, the stopping distance will be longer. The skid mark would be longer. Is longer on the moon. Because gravity is higher. Oops, I didn't mean to say that. Gravity is less. And therefore delta x is more. So that's an inverse proportion. That's how you write an inverse proportion. One is less, the other is more. Okay, and now let's go back to continue on. We did that already. 10. Now we're on to, determining the braking skidding distance. So I guess these are now. So, I don't know that I want to take the time to get the answers, but where for like number 10, it says determine the distance. You would just plug the numbers in. So I think the original problem said the car was moving in with a speed of 30 meters per second, I think. Yep. So you would just plug all those numbers in. You end up with 30 squared, 2 times 9.8, oops, times 0.8, I meant to say times 9.8. So if you were trying to solve for that stopping distance, I'm just pointing out, you would stick all those numbers in. 30 was the initial speed. 0.8 was the coefficient of friction. Sorry, that was a little messy there, 0.8. And then G is 9.8. You would just plug those. I crossed them out only before because I was trying to find out the proportion, but the actual formula is all of those things. So I guess I can do that. 2 times 0.8 times 9.8. And then 30 squared is 900 divided by 15.68. 57.4 I get. A little over half a football field. That speed of 30 meters per second, by the way, that's about 70 miles per hour. So yeah, that sounds about right. You're going at 70 miles per hour and you slam on your brakes, yeah, you're probably going to be skidding about half a football field or even more before your car stops. Hopefully there's nothing in that distance because you ain't going to be able to stop any sooner than that. Okay, let's continue on. If the original car was traveling twice as fast, by what factor would the stopping distance change by? Now we're asked to analyze the connection between stopping distance and how fast you're moving before you jammed on your brakes. Write the same formula down that we derived. They're asking you, how does the original speed you had before you slammed on your brakes affect the stopping distance? Well, assuming that we're talking the same tires and the same planet, then this is our proportion. Delta x is proportional to the initial velocity squared. What does that mean? When there's a square relationship, that means doubling VI, like 60 meters per second instead of 30 meters per second, come in twice as fast, like 140 miles per hour instead of 70 miles per hour. How much longer will the stopping distance be? Well, I'm imagining putting a 2 there since I'm doubling that initial speed, but I have to square it 4 times further. So you will actually slide not half of a football field, 4 times of a half, which is 2 football fields. You come in at 140 miles per hour with these tires and slam on your brakes and skid, will skid the length of 2 football fields before you stop. Wow. 4 times as far when you just double the speed? Yep. It's an energy thing. Just a FYI that remember kinetic energy is 1/2 mv squared. Same idea. Kinetic energy is proportional to v squared. So doubling your speed quadruples your kinetic energy because kinetic energy is proportional to v squared. That's the reason. You got 4 times as much energy, you'll go 4 times further. That was that one. Now we're moving on to, hopefully it's just, I think it's just a couple more and then we'll be done. It'll take a little while, but you guys need to learn these things and this is just the way we're doing it. All right, drive a formula, number 12, drive a formula for the braking skidding time. Number 12. How long will it take this car to literally stop in seconds? Well, if you're mentioning seconds, then we got to pick a formula that has, I mean, you could think just this really. A equals delta V over delta T. You could think of that. I mean, it involves an acceleration, a change in velocity, and a change in time, how long it takes. You could even have written that same formula this way. This is the same 2 formulas, just written in different ways. We know the final velocity is 0. We talked about that because it stops, car stops. We know the initial velocity was originally 30 meters per second. And we know the acceleration was mu k times g. We did that way back in the beginning, right? Percentage of g. Now, technically, this would have been a negative here. I always forget to put the negative, but I'm adding it. So it would be negative again because it was a force of friction was to the left, which is negative, and therefore the acceleration will be negative. And then this, when it's moved over to the other side, the initial would come over as a, like before, a negative. And then you're like, oh, wait, there's 2 negatives there, so they would cancel. That's right. And now we're solving for t. How many seconds will it take for you to stop? Solve for t algebraically, just divide both sides by mu k times g. This is the stopping time. So I had to pick a formula again that had time in it because that's what the question was. How many seconds does the skid last? Couldn't have been the other formula because that one doesn't have time in it, right? There's no time inside this one. Just a distance. That's why we chose that, because that was about stopping distance. This is about stopping time, so we need something that has time in it. And we can see there's relationships there again, right? T is proportional to your initial velocity. That means if you come in twice as fast, it'll take you twice as many seconds to stop. And you can also see the stopping time is inversely proportional to mu, the coefficient of friction. So on a rainy day, when the coefficient is less because of rain, you're going to have more time to stop. It'll take you more seconds of stopping. That means you'll go further before you stop. That's why it's dangerous. Don't go too fast on a rainy day. So that's that one. And then the last, the formula it was asked was right here. And the very last part is determine the braking time. We would just plug those numbers in. It would have been 30 divided by 0.8 for mu times 9.8. .8 times 9.8. 30 divided by 7.84. Get 3.83 seconds when I did that. The stopping time. A little under 4 seconds. Then the next question, I think near the last question, said if you doubled the coefficient of friction, what would happen to that amount of time? Yeah. If it was moving if it was moving 2 times faster, by what factor would the braking time change by? If I doubled this to the number 60, I'd get twice as much. If I did 60 meters per second for the initial speed instead, divided by the same number, I'd get double that. I get 7.65 seconds. It would take 2 times longer to stop if you're going twice as fast. All right, and then the very last part was, what would these graphs look like? What do these graphs look like? For position versus time, for velocity versus time, for acceleration versus time. Well, remember, we know that the car is slowing down, right? It has to have some curve to it because it's decelerating. Anytime there's a speed up or a slow down, we call that acceleration. The position versus time graph has to be curved. So that one's going to look like that, right? Where the slope, remember that the slope has to become less because the slope represents the velocity. So this decreasing slope means decreasing velocity. Technically, that curve would have to come all the way out to becoming flat, like that, where the slope becomes 0. The final velocity is 0 and the slope becomes 0. So that's what the position versus time graph would look like. A velocity versus time graph would decrease linearly until it stopped. This has, again, been the rule all along. For constant accelerations, whether it's speeding up or slowing down, the position versus time graph is curved, the velocities has a linear effect, and the acceleration is constant, but in this case, it's negative. So those negative values would be down here. I don't know what the value was. Mu times g, what was 0.8 times g? 7.84, so this was negative 7.84. So during that skid, it's a constant acceleration. I'm going to point out that that's not intuitive. Most people think that the faster you're moving, the more the deceleration rate would be, or if you were sliding at a slow speed, it would be less deceleration rate. Actually, it's a constant deceleration rate. The force of friction is constant, and the deceleration rate is constant. Right, and then that should be the last question. If a car has twice the mass of the original car, by what factor will the braking force in the newly designed braking system have to increase by? Well, that's going to take a little bit. I don't know if I want to take another 5 minutes to do that. I think I'm just going to post that one. I'll post that one online because I'd rather just move forward. So that's a lot, and that's a while for me to do that. But you know, that is what it is. You guys need to kind of move forward with this topic. I'm now going to have you guys work in groups. If you can take out your Chromebooks. Although, oh no, it's only 15 minutes. Well, there'll be enough time for you to do that. I think I'm just going to give you a problem to work on then. There's only 15 minutes remaining. Oop, I don't know why that just happened. So let me give you something to work on, and then moving forward, I'm going to have to start giving you solution guides. So just pointing that out. I wanted to do one in full like that for a class, just to kind of, you can see all the mechanics of how that works. But with the time that we have this year to try to get through this material, I can't possibly do that all the time. So moving forward, I think what I'm going to start doing is just posting the solution guides online, and you can review them. I usually do that again at the beginning of a topic. I'll kind of do a thorough review, but we're going to have to start doing more of the guides. Ask questions if you have them. All right. Give you a quick question that you can try. Right. Oh, I see. Because it was confusing me. I'd like you to try something that's a little bit different. Give it a try. Let's say there's I don't know, maybe make it a little longer. Maybe this is some sort of boat. And it has two ropes pulling on it. It's like a top-down view of a top view. The top view of a boat. There's a rope pulling on it that way, and a rope pulling on it this way. So you're just a bird looking down on the ocean, and you see some machine is pulling a boat. I mean, maybe there's some, I don't know, some larger boat ahead of it. I guess that could be the case. Some giant boat, like a tugboat, and it's got two ropes that are going back like this, tied to a smaller boat. It's dragging this, tugging the smaller boat. This angle would be shown as theta, symmetrical on both sides. So let's try this question, which is, assuming that the boat, assuming boat is moving at a constant speed, not like, when you look at boats like this, they're not accelerating, they're just going along at a fixed speed. Assuming the boat is moving at a constant speed, hard. And that the amount of force in both ropes is F, and force in each, really tension force, by the way. When you have force in a rope, it's called tension. And tension force in each rope is F. Determine an expression for the drag force from the water. So I'm going to point out that drag isn't only a force we use to talk about how air, like a car driving forward, feels air pushing it backwards. Call that drag also. But if you're a boat person, that a captain, the water moving underneath the boat is kind of sliding and dragging along the bottom of the boat. While your boat moves forward, there's water moving backwards, right? That sliding effect drags on the boat and provides a backwards force, much like friction or air resistance. It's a resistive force. Call it drag. So this is one you can try. That's it. See if you can create a formula for the drag force from the water as it relates to these two forces that are pulling it in this direction. I will point that out. These are forces like this. And I'll also give the other hint that the drag force is back like this. Like I said, it's the water that's flowing underneath it is causing the boat to feel like it's being pulled back. It's the drag force. And now we have two ropes pulling it forward like this and this. That's the most I probably would say to you. Just remembering that if something's going at a constant speed, that means it's not accelerating. And if it's not accelerating, it means that the net force is zero. Net Newton's second law that's the idea that if something's not accelerating, it's moving at a fixed speed, the acceleration is zero. And therefore, if the acceleration is zero, then the net force must also be zero. It doesn't mean that there's no force, it just means the net force. They must all add up to zero. And I'll also provide one more image. This is going to be probably part of your homework to do. Try. That these two forces have components, not surprisingly. There's an x component to it and a y component to it. We call this Fx, and this is Fy. And this rope that's pulling at this angle also has an Fx and an Fy. So when you're pulling on something at an angle like this, there's two components. There's a sideways pulling force, effectively from pulling at an angle, and an upward pulling force. This upward pulling force is what's going to actually pull the boat forward, right? It's these two Fy components. They're going to pull it forward. And then remember the drag force, which was down, is like this. So I'm giving you the full vector view there and thinking, can you come up with an expression? You got to remember that involves an angle. I am going to point out that my angle in this picture is actually here, drawn to the vertical, which is not common. So you got to be aware of that. AP would do the same thing to you. For some problems, they draw the angle to the vertical. Usually it's the horizontal, but not always. Just pointing that out. This angle here is not the same as that angle there. Right? I was drawing this angle here over here. This angle. You can think about it, give it a try. Just remember, I'll also point out that for constant speed motion, the net force is equal to zero. That means however many forces you have that you're adding up, force 1 plus force 2 plus force 3, however many you have, they all add up to zero. That's how you write that. I'm not saying that you would just write it like that. I'm just saying it's in general, just recognizing that X forces are battling against each other. X forces, this force fights against this force. What are the vertical forces doing? These guys are on the same team. They're both pulling forward, pulling the boat ahead. Who are they battling against? They're battling against this guy here. He's trying to drag the boat back, the water. The ropes are trying to pull it forward. So you always compare vertical forces. Those would have to add up to zero, right? These upwards together have to add up to this downwards. Because that's the idea, that the net force has to be zero. When we say the net force has to be zero, it means that the net y component forces have to add up to zero, and the net x component forces have to add up to zero. We're back to this two-dimensional idea where we have to do all vertical or all horizontal. That means both of these added together have to be in balance with this one so that they add up to 0. And both of the x components must add up to 0 because they have to be balanced also. Because you know your boat's not moving right or left, it's just moving forward. That means these two must be a cancellation effect. If you can use those ideas, you try to see if you can get this expression for the drag force. Has to be equal to the two of these added together. All right. And on Thursday when I see you guys, probably going to be make sure you do come in with your Chromebooks, like I'm sure you always do. I had to do that review for that one. I'm not going to be giving homework beyond this one problem. I'm going to give you guys a lot of the classwork in the breakout rooms on Thursday, probably like 3 per group for most of the class. I'll have an assignment on Google Classroom. So be prepared to have something like earbuds and Chromebook. You might very well be paired with somebody at home. You know, doesn't mean that you have to be paired with somebody in here. You can be in a group of people at home. And I'll be essentially moving around from the room. I'm going to try to dive into that right away in the beginning of class, so we have plenty of time to do that. And I'll be moving around the rooms to try to help students, help groups out with some of the problems. And I will also post everything that I did today, like the notes, not the video, yeah, but I will take photos of all of the notes and the solutions to the homework assignment, and I'll take a photo of this, and I will post all of those Google Classrooms. Also, I might actually be done grading the exams by the end of today's class day. Gotten through about half of them. So might very well have the test grades going up by the end of the day, as an FYI. So again, I am going to be posting the solutions to the last problem, this problem. I might add one more small problem, but the intention is to have not a lot of homework so that on Thursday, you guys can more or less spend the entire time doing some work together in groups. So I'll be posting this. Everybody in here has a Chromebook, right? You have a Chromebook? And you have you have a Chromebook that's working? Okay. Students at home. We are closing out, so I'll say goodbye to you. And I'll see you guys on Thursday. Bye-bye. Have a good one. Sorry I can't see you guys, but I'll wave down here. Bye-bye. Have a good day, guys. Yeah, but like I said, I can technically change it. It depends on, what you want. Give me 1 second. Let me just close this out.